So as we look at how drag depends on certain factors, just quickly let's talk a little bit about Reynolds number and its effect on drag. Now typically drag, you're going to have to find the coefficient of drag, you need the drag force. To get the drag force, you need the coefficient of drag. You can get the drag force by going and doing an experiment, finding it out, and then you can calculate out what its coefficient of drag is. So typically what you'll need to do is you'll need to take a look at what's going on in a textbook and go, okay, well, I'm just going to assume that it's a cylinder. Okay, coefficient drag of a cylinder is 0.8. Oh, I'm looking at a flat plate. Coefficient drag of flat plate was 1.1. In certain cases, you can actually calculate out exactly what the coefficient of drag is, but it's very, very corner case, very small amounts of areas. One of these places is what we call creeping flow. Now, creeping flow is, you'll also hear this called Stokes flow. It is named after Stokes, who is one of the biggest names in fluids. There's equations called the Navier-Stokes equations. He was one of the people that came up with it. It's probably one of the big unifying equations in fluids. Unfortunately, we do not learn about it in this class. I like the stuff a lot, but then again, I like differential math. But Stokes, and he was from the 1850s. Navier-Stokes equations are great. It relates motion, inertia, and pressure and viscous forces. But he found that for very small Reynolds numbers, and this creeping flow, the Stokes flow, when I'm looking at a Reynolds number less than 1, we have found that the acceleration terms in the Navier-Stokes equations become negligible. So creeping flow is only based on the pressure and viscous forces. I actually used this in my PhD dissertation, which was kind of nice. But so what does that mean for us? Well, that means that when we have this case, when my Reynolds number is less than 1, I can calculate out exactly what the coefficient of drag is going to be. So for a sphere, that coefficient of drag would be 24 over the Reynolds number based on diameter. That's only for a sphere, and it's only for creeping flow. Now, if you take a look at it in your book, the version of the book could be table 7.3 on 489, and that's 7.2, and then 7.3 and 491 will give you the coefficient of drag on a sphere. But one thing that you're going to see is once you hit a Reynolds number of greater than 10 to the 4th, that coefficient drag stops being dependent on the Reynolds number and kind of settles out, because it's beyond the point where you're worrying about how those inertia and viscous effects are balanced with each other. And that's about it. This one's a short one. There may or may not be the example problem for this. It depends on, once I finish everything else, if we've got room in the thing for this problem. But it's pretty neat. So when you're less than Reynolds number 1, you can calculate out exactly what the sphere coefficient of drag is.